Hello everyone, this is a presentation for our CVPR work, Natural Language Assisted Sign Language Recognition. Now let me give an introduction of our work. Sign language is the primary communication method among the deaf communities. Sign language recognition, SLR, can help to bridge the communication gap between the hearing impaired and normal hearing people. SLR is also the most basic task among the sign language understanding community. We empirically find there exists a majority number of visually indistinguishable signs, whereas signs among the current widely adopted sign language recognition benchmarks. We can categorize the VI signs into the below two types. The first type of VI signs is with similar semantic meanings. For example, the sun, cold, and winter look similar, and their semantic meanings are also similar to each other. The second type is VI signs with distinct semantic meanings. For example, the sun, table, and afternoon are quite different in terms of semantic meanings, but they still look similar to each other. In this paper, we propose two techniques to address the above two types of VI signs. First, for VI signs with similar semantic meanings, we think that assigning hard labels to them may hinder model training. So we propose a language-aware label smoothing, which assigns biased smoothing weights to VI signs, considering the gloss similarities. For VI signs with distinct semantic meanings, although it's challenging to classify these VI signs from the perspective of vision, their glosses are still distinguishable. So during training, we blend the vision feature with the gloss features from the whole vocabulary and optimize the model with the proposed blended labels. In this way, we can maximize the signs separability with the help of gloss semantics. Here is an overview of our framework. We first feed two pairs with different lengths to our backbone network. Following previous works, we model both RGB videos and keep-on heat maps. We temporarily crop a 32-frame pair from the original 64-frame ones. In this way, we can improve the model generalization capability. We also propose a backbone network, video keep-on network, to model both pairs with different lengths and different modalities, RGB videos, and keep-on heat maps. The extracted vision feature will be further fed into our head network, which consists of two parts. The first one is a traditional classification layer, but optimized by our proposed language-aware soft labels. And the second part is the proposed intermodality mix-up, which aims for auxiliary training and can be removed during inference. Here is an illustration of our backbone network, WikiNet. It consists of two subnetworks, WikiNet 64 and WikiNet 32, taking video keep-on pairs with different lengths as inputs. Each subnetwork has a two-stream architecture, consists of two S3D networks to model both RGB videos and keep-on heat maps. Following previous works, we also insert bidirectional lateral connections after the first 4 blocks of the S3D network. The output features will be fed into their own head networks to compute losses. Here, this figure shows the architecture of our head network. Generally, it consists of two parts. The first one is our language-aware label smoothing. Given a gloss label, for example, 20, we first use fast text to extract its gloss feature. Then we compute a normalized cosine similarity between the GT gloss feature with those of the whole vocabulary. Then we use a softmax to normalize the similarities to obtain the soft labels, which will be used to optimize the primary classifier FC1. And the second pass is the intermodality mix-up. We blend the vision feature with the gloss features from the vocabulary to the intermodality features. It will be fed into the auxiliary classifier FC2 and will be optimized by the intermodality labels. Note that the intermodality mix-up is simply for auxiliary training, and thus FC2 can be removed during inference. However, we think that FC2, the well-optimized FC2 contains knowledge of classifying signs with the help of natural language information. So we further devise a classifier integration to propagate more information from FC2 to FC1, which is the solely classifier for inference. Here we show that our proposed method can achieve total performance on two widely adopted benchmarks, MS-ASL and WL-ASL. It's also worth mentioning that we can achieve total performance on all of the subspecies with different vocabulary size. Here we show several evaluation studies. First, we validate the effectiveness of the major components, language-aware label smoothing, and sign mix-up. Our sign mix-up consists of two components, intro-modality mix-up that we apply vanilla mix-up onto both RGB videos and K-point heat maps, and the proposed intermodality mix-up. We also provide quantitative results on VI signs, so we can clearly see that our language-aware label smoothing is quite effective on VI signs with similar semantic meanings. But our intermodality mix-up is the most effective technique on the VI signs with distinct semantic meanings. And using both of them can achieve the best overall accuracy. That's all. Thank you for your listening.